Okay, sorry. Okay, so my name is Jiangping from Institute of Physics. I would first thank organizer to invite me here to give this talk. So Stephen just talking about this Kagome lattice. I think he gave a very good review of this. So I will try to talk about this particular interesting thing could happen in Kagome lattice, which called loop current order. So go yeah. So here's the outline of my talk. So first I will give the introduction, then I will talk about what is the loop current order, and especially our focus in the loop current order in these Kagome lattices. And I will discuss some theoretical models which can provide this loop current order, and then I make a summary. So we know the magnetism. We study lots of quantum magnets, and all these Kagome lattice study is related to the spin liquid physics. So we are often dealing with like the spin degree of freedom, right? So that's we based for study the magnetism. There's also another thing we can give you magnetism. We know from the standard textbook. We know that it's from the electric current. Right? So we know this this Ampere's law. When we are loop current, you produce this magnetic field. Okay. So the electric current, electric current is also another degree of freedom which can provide this quantum magnetism, of course. But this hasn't been studied very, deeply in kinetic matter physics, especially in the microscopic models. So if you look at the electric current, right, this is actually a very simple design. A simple definition, which is if you have a Hamiltonian, you to do the partial derivative to the vector potential, you got the electric current. In a lattice model, you can just write down this electric current, by hopping like this on a bond. So for the kinetic physicist, we are really interested in this question is whether the electric current can be non-zero in a ground state. Okay, that's a key question we try to address, and this is the main topic we'll focus on this talk. So in fact, it's if you look at history, it's quite interesting. Whether this electric current can be non-zero at the ground state, actually, it's in very early days. Landau is already asking these questions, and he, in fact, if you look at the in early days, and his Landau's first theory of superconductivity, actually, what he proposed is about the electric current. So he write down this free energy like this, and this J is actually electric current, and which he basically conjecture guessed that the superconducting transition is that the electric current become non-zero at the ground when superconducting transition happens. Okay. That happens in 1933, actually, very early days. And this, I think, traced back is probably the first idea which proposes this electric current can be non-zero at the ground state. But of course, certainly we know that this is not true. Of course, so in the after we know that not these days, of course. But this is not true. It's actually related to very interesting theorem called the Blocher theorem. So we know if you study solid state physics, everybody knows Bloch theorem, which is related to periodic potentials, right? So you solve the wave functions, everything, and also band structure is based on the Bloch's theorem. Actually, that theorem is called Bloch's second theorem. So, but actually, Bloch has this first theorem, which actually basically stated like this. Okay, so electric current, in the ground state must be zero. So this is actually the global electric current means like you can say ferroelectric current, like like ferromagnetic, ferroelectric current in the ground state must be zero. Okay, you cannot have if you so you can prove it just by disprove if you have current global current at the ground state, you can actually construct another state which has low energy than this one. So that's very easy to to prove it. And this was taking place, also many similar, almost the same time as Landau's proposal on superconductivity. So you immediately know that this Bloch's first theorem actually, kills Landau's superconducting theory, first theory on superconductivity. So because Landau's proposal conjecture on this current will be in a zero ground state, it violates Bloch's first theorem. Okay, so that's, I think, is the first story which you can make. In fact, this Bloch theorem can apply to multi-fluids. Okay, so I'm going to talk about the one actually very early days. I noticed this, which is called the second type of multi-fluids, which basically means magnetism induce ferroelectricity. So if you think about how the magnetism induce ferroelectricity, you can actually write down this single electron, and you Hamiltonian, and you calculate the electric current. The electric current has three terms. One is it's a standard paramagnetic current, and then also we have this magnetization current, and we have also a spin orbital coupling. You will have this current induced by spin orbital coupling. Okay, so in an insulator like multi-fluids, is the insulator, the paramagnetic current vanishes. Okay, so but if you want have this still satisfies Bloch's first theorem, then you left with the electric current by SOC and spin orbital coupling, and the electric current by the magnetization must be added together to also vanish. Okay, so this you immediately reach to a equation like this. Okay, so you have a magnetization curve, and magnetization times cross this potential derivative must be vanished. So you can immediately the potential derivative is a polarization. Okay, the ferroelectricity, and you can immediately derive the ferroelectricity has this type of forms in this type multi-fluids. Okay, so if you have magnetization and you have this formula, you will induce the ferroelectricity, and you add some other argument where you want to make this to be insulating, and then you immediately actually can derive that the ferroelectricity in this type system induced by magnetization actually has a limit, like this. And this limit actually exactly explains like why so far we actually this rare earth manganese oxide has just below the limit. Okay, so that's actually quite in this case. Okay, and this formula also explains the what type magnetization can induce ferroelectricity, like this. This magnetization has to be helical. Okay, so if you have helical magnetization, and you can induce this ferroelectricity. Okay, so that ferroelectricity is is a global value. So that's as the formula explains this. So this simple Bloch-First theorem actually can help help us to understand the second type multifluidics, and you can explain how the relation between the magnetism and the ferroelectricity just by state that the electric current has to be vanished. The global electric current has to be vanished under the ground state. Okay, that's simply a statement, but we know that just this first theorem is just says the global electric current has to be vanished, but it does not tell you whether you can have local electric current order. Okay, so if you have local electric current, means you can have some pattern based on the local electric current if only in the ground state. That we don't have mathematics to prove this cannot be exist. Okay, but of course, experiments so far, we also do not know whether we have a system actually have this current order yet. Okay, of course, the Kagome lattice so far shows some promising, but now we haven't find a system in the nature. So so let me go to introduce the loop current order. So if we look at the loop current order and compare with charge density wave, okay, like this. So we all take it on the bond. So like an electric current on the bond is actually like this, and this is the charge order on the bond. Okay. So if you have charge order, this B will be not zero, and this if you loop current order, it will be not zero. So if you look at these two formula, you can immediately realize actually the hopping value in the loop current order is pure imaginary, and in charge order is real. So of course, it's imaginary. The electric current, certainly breaks time reversal symmetry, and the charge order still conserve time reversal symmetry. So in another way, you can view the loop current order is that the loop current order is just imaginary charge density wave. So it's a charge density wave went to imaginary channel. You become the loop current order. That's another way to view, the loop current order. So if you look at the literature, the loop current order first proposed is actually in the couplets. Okay, so in the very early days, Maston, Afric, they started this strong correlated model. They discovered there's a Coulomb flux phase, okay, like this. Okay, so this is a real electric current and running on this bond. And this Coulomb flux phase was later was used to explain this couplet this pseudo gap phase by Chakravarti, Chetanayaka, and Babalofin. So they called another name, which you call the D-density wave. Okay, so this loop current order, if you write down in this momentum channel, and you really have this K plus Q as non-zero, and you have the D wave factor like cosine Ks minus cosine Ky and imaginary. Okay, and that I think this topic is the D-density wave was started around 2001, 2002 is a very hard topic. Okay, but as of course later we do not have smoking evidence to support this in the couplets, but this is certainly one very interesting idea which has been generated in study of cuprates. So there's also loop current order was proposed by Chandravarma, and then later in 2010, like around that time. And so his proposal for the cuprates is slightly a little bit different from this d-density wave. D-density wave basically everything you write written in copper atoms. So this is the model is reduced to a copper side. But in this Chandra's proposal is that as a loop current order is actually hidden in this one unit cell. Okay, so this loop current or cuprate does not violate does not break the translational symmetry, lattice translational symmetry. So it's hidden in the each unit cell. Okay, so the key observation will be this will only break the time reversal symmetry, no translational symmetry break. And this has also been get some support from neutron scattering, but overall it's still an unsettled issue. Right? This whether this is true or not in cuprates is still unsettled issue. But these two proposals was really generated through study in cuprates in correlated electron systems. Very interesting idea. And so recently, actually, we, Stephen has already mentioned there's many experimental evidence which is thinking that these 135 Kagome superconductors maybe have some time reversal symmetry breaking. Okay? And so without magnetism and you have this joint time reversal symmetry breaking, we immediately realize that could be actually loop current order happening in this Kagome lattice. And it has been proposed very earlier, this could be actually have this loop current patterns. This is probably the most favored one in this for this 1,3 Kagome lattices. So this Kagome lattice 135, and I think Stephen has given very, very nice introduction. So I will not go to talk about too much. So this is vanadium for this Kagome lattice, and this has various CTW order. Also have superconductivity, also have pneumatism, many interesting things. All this has been detected in this 135 system. And the first evidence which show maybe there's some time reversal symmetry breaking is observed by the Zahir's group, which you have this unconventional chiral charge order in Kagome lattice. And when they measure this STN, the peak, there's a chirality, and this chirality can be manipulated by the magnetic field. So that's the idea. Maybe that tells you that this charge order is very, very special. Okay, so and later, of course, there's many experiments I will not go to discuss very detail. And so if you look at the system, there's also mu-SR curve effect measurement. I think Stephen also mentioned this. So no, there's many experiments now. Most experiment actually show that there's time reversal symmetry break. Okay. But there are also some experiment results are kind of controversial. For example, the curve effect signal was kind of controversial. Some group see it, some group didn't see it, and it's still not resolved the issue yet. But here today I wanted really focusing on the theoretical part. So not going to go to this provide a review on this. I think Stephen already, other people will give this. Of course, Kagome lattice now is a Kagome material, right? It's becoming a field of called Kagome material. There are many Kagome material has been discovered, and they all have very interesting physics. And from started early the quantum magnets to many systems. Okay, so I skip this. So here the question for theorists I want to really try to ask is, can we have a theoretical model in Kagome lattice actually has some loop current order in the ground state? That's the key question I wanted to address. And so whether we can really have a theoretical model on this. So far, it's not easy. Actually, it's the loop current order is not easy to get from realistic models. So if you go to look at this, actually, the early days, already people started like in Kagome lattice, just you think about one band, and you have the standard, the correlated electron system model, like a Hubbard turn and nearest neighbor interaction. You put it there, and you try to solve this model, find their, the ground state, different orders, and draw their phase diagrams like this U and V. In fact, we do not find any loop current order state. So you have, CDW, you have CDW, SDW, all this you can find even superconducting ferroelectricity. So based on the on-site Hubbard interaction and the nearest neighbor the positive interaction, you actually cannot get this this loop current order state as a ground state. So here actually recently we take it even further, which is we think about a spinless Kagome extend Hubbard model. So basically we think about a spinless electron, and we have nearest neighbor interaction and a second nearest neighbor interaction. And we find that if you use a second nearest neighbor interaction is dominating, it's important. Actually, we have this loop current order. So like this. Okay, so in the second nearest neighbor interaction became important. This is a phase diagram here, and this is the main result for on this. Okay, let me go discuss a little bit details on these models. So we know the Kagome lattice is very special. It's you can divide the Kagome lattice by 3 triangle lattices, right? So you have this Van Have singularity point, which is actually located this at the end point in the brain zone. Okay, so you have 3 Van Have singularity points, 3 endpoint. And if you look at this Van Have singularity point, actually also have very interesting. Actually, this contribution to this Van Have singularity point is actually related to, can be in respect to each sublattice, each triangle sublattice. So there's a real space and momentum space corresponding at this Van Have singularity point, and this is very special for this Kagome lattice. So we can look at this lattice, and we can calculate all these kind of different order susceptibilities, and you can also use the symmetry to classify each orders. And of course, here we limited it to ourselves, just allowed to just translational symmetry breaking by 1 unit cell. Okay, so you can classify these symmetries. In particular, you have charge order, bond order, and they will correspond to another if you become antisymmetric, they just become the the current orders, especially this 3Q order, this the star, okay, charge density wave is related to this 3Q imaginary order, which is the loop current order we draw on opposed to the early days. So that's based on symmetry, and you can nicely do these susceptibility calculations, and one side and one is bond. One is bond, you can distinguish this real channel and imaginary channel. Real channel is pi, and the imaginary part is Kasi. Okay, so that's you can do these Hodge-Fock interactions, and so you have this real channel and imaginary channel, and you have the form factor, and the form factor you can look at this for this lattice, and you can immediately find that the very importantly is that the second neighbor interactions is NMM bonds actually actually favors these imaginary bond fluctuations. Okay, so the next neighbor favor as a real bond fluctuation, but the second next interaction is favoring these imaginary bond fluctuations. So so this is very intriguing. So that if you have strong enough this second nearest neighbor interaction, and it can favor this loop current order. So you can put this Hodge-Fock stop PA calculations, and you can immediately find that when you have second nearest neighbor and the second nearest neighbor interactions, actually you will have draw these three faces. Okay, so so basically when you have these nearest neighbor interactions, you go you will get the center bonded order, charge bonded order, and if you have the nearest neighbor, second nearest neighbor interaction dominant, you will get a loop current, and if they are both are very strong, you will just get the another CDW, two-folded CDW here. This is a RPA calculation. Probably you think RPA is not so reliable. So we went to this functional normalization group analysis, and we did like massive calculations, and calculate all this stuff, the instability of these all these orders, okay, different type of orders we put here, and we find that indeed, this loop current order is the most his instability is happening at this second and next neighbor interaction can be important during these phase diagrams. Okay. So you can also construct, based on this, you can construct the Ginsburg-Landau free energy analysis. So in which case, depends on these parameters in this Landau-Ginsburg free energy, you can construct that what kind what kind of parameter allow you have this loop current free energy. So this is a simple. We can divide these three sublattice, as you said, and you can make these three sublattice their interactions, and you will find whether C2 is less than 0, and this will favor these 3Q loop current order phase like this. So another way you can also try to understand is that simply just by gaining, what kind of energy gain you can have in this loop current order to get the idea, why this second and next neighbor is favoring this loop current order. Okay, so so in fact, you can if you look at the gap opening at the Fermi surface, a next neighbor interaction. Actually, favors this charge bond order is uniformly open gap. But for the loop current order, is actually if you have the second nearest neighbor interaction and open a very large gap along this endpoint. Okay, so when you have this Van Have singularity, located at this endpoint, actually this second nearest neighbor repulsive interaction can open a very large gap and favor this loop current order. Okay, so that's a very simply, can understand the physics. I think so. So if you realize, this analyze actually is behind this analyze is because you have these 3 sublattice, and you create these 3 Van Have singularities, and if you have second repulsive interaction, and you can favor these imaginary charge density waves. Okay, this is so if you thinking about this with this Kagome lattice, we talked about the spin liquid is that you have these 3 spins, you got fluctuations, and why you can think about the 3 is very important because if you think about the simple C3 group, you have these complex representations. You can have imaginary, that's a thing. Of course, in high energy, you have SU3. These 3 numbers is very important. The Kagome lattice, I think, is 3 sublattice. These fluctuations can lead to us to the loop current order. So. So in summary, I think if you have these Kagome lattice with the Fermi surface near Van Have singularity, actually can enhance this loop current fluctuation to lead to loop current states, ground state, and it's the next neighbor interaction, and this 3 sublattice of Kagome structure. I think is combined together. It's very critical in driving the loop current order, and this kind of physics maybe you can also study in other type of lattice, for example, Lieb lattice, or these different cases. But I think the key will be very similar if you want to drive the system to a loop current order. So finally, I would like to thank my collaborators. Jiang is from IOP and is in my group, and Xinxin Wu is from Institute of Theoretical Physics in Chinese Academy of Science, my former student, and he does these functional RG type of calculations. And I have another 3 students which involving this research project. We also have strong collaboration with Ziqiang Wan from Boston College and Yin Zhang from this Kavli Institute of Theoretical Science in the Academy of Science. And thank you for your attention.
Yeah, thank you, Jiangping. Any questions? We have time for a couple of quick questions. Yeah. Yeah.
Hello, hello.
Yeah.
Can you hear me? Yes?
Yeah.
Okay. Thanks, Jiangping, for an interesting talk. This is Brian Anderson. I just have an obvious question. Your model is spinless.
Yeah.
There's some argument or some way of arguing for the relevance of that for the 135 materials. Because I think if you include the spin, you probably get magnetism instead, right?
Yeah. You are absolutely right. So we are, still doing this calculation on these spin-4 models, including the second neighbor interactions. So the calculation is quite messy now. because so many orders you can construct it, So we're still doing these calculations. So far hasn't finished yet. So here what I try to really trying to find one model which you can absolutely sure that you have this loop current water. That's the first step. So the second step, of course, you want it to be more realistic models that can get this. Yeah.
Okay, thank you.
So I have one.
Yeah.
Can you hear me? Hello.
Yeah. You go ahead.
I have one question that you told that there are some loop current in Kagome lattice. So because of this loop current, is there any possibility that local magnetic field is arising, and is there any effect of that magnetic field because of the loop?
Yeah. Certainly, if you have loop current water, so the way you detect, it should have very small magnetization, right? So moment is very small. So far, some mu SI, they actually claim they shows they see it, some see it, right? Some, but the experiment result is kind of messy. So another way is also important is that you have multi layers. So here we are talking about one layer models, right? So 2 layers. So if you have 2 layers, the top one, bottom one, they are the current could be opposite, and the moment is actually become even more smaller, right? In that case. So you need to really do very careful experiment, although very good materials to really make people believe or convince people. So that's the difficulty, I think. Certainly, there's some evidence which has time reversal symmetry breaking, right? So I think if you have time reversal symmetry breaking, and if you do not have the spin magnetism happen, and it's very likely it's related to the loop current. So that's another way you can take. Yeah.
Okay, thank you very much.
Okay, then if there are no further questions, let's start Jiangping
Wait.
again.
Oh, wait, can I ask one real fast? Sorry.
Yeah.
Can you hear me?
Sure.
Yeah,
Yeah,
yes.
sorry. Sorry, I couldn't figure out how to raise my hand on the Zoom.
Sure, please go ahead. Please.
I have maybe a really naive question, Jiangping. So since the 3 sublattice is so special, right? Is there any parameter regime where a similar phase can occur on a triangular lattice?
Yeah,
For the loop current.
So for the simple, like next neighbor and second next neighbor, we don't see it actually. My student also did that, in this drawing. But I think you can add more. Certainly, it's possible. So, yeah, for simple models, we don't see it. Yeah, well, I can only
Okay.
tell you that. Yeah.
All right, thanks.
Any more questions from other online participants? Okay, it seems not to be the case. So then let's thank Jiangping again for a very interesting.
Thank you.
And we convene now outside for a photo session, and then followed by a coffee break. And then we meet again, maybe, if it's okay with you, Brian, maybe 10 minutes later than scheduled. So let's be here at like 10:50, around that time. Okay, then let's move outside. Yeah. Thank you, everyone, for the interactive sessions.